Okay, I guess we can get started. So, welcome back to the afternoon session. Thank you all for joining. Um, so, our next speaker is Professor Eldad Haber from the University of British Columbia, and he's going to tell us about active learning and optimal experimental design.
So thank you very much for this organizing this thing, and thank you all for really logging in at this time. I know it's not necessarily the most convenient that it can be. I'm going to really talk about work we've done that is not so much about optimal mass transport. There is a little bit of that kind of hidden in the background, but it's really more about active learning and experimental design. And of course, we started doing this, to be honest, over a year and a half ago when I saw some lectures by Andrew Stewart. Really was the person that kind of motivated me to think about this problem again. And then when the COVID started, it's actually something that kind of came into life because there was this issue about testing, and we hear it still, like, who should we test? How much should we test? And this kind of all links to the question of optimal experimental design, and hopefully you'll see. So again, I'll motivate you, I'll give some background and talk about semi-supervised learning, graphical methods, and then I'll go how we actually look at it from semi-supervised learning to active learning, and talk a little bit about numerical solution, maybe an example or two, and conclude with this. So here's like one of the motivations that we see. That's a very clear motivation for today, that we realize that we need to do a lot more testing. The problem is that if we want to test in principle, we would like to test everyone. If you think about it, like the best scenario that we could have is that everybody in the morning would wake up in the morning, have a test, know if they're sick or not sick, or if they're infectious or not infectious, and decide if they're staying in bed or going to work. I know most of us will stay in bed, but it's, still, I mean, that's one of the desired things we want to do. The problem is, as always, that we don't really have enough tests. So it doesn't matter what we do, we're not going to have 360 million tests a day. It's not going to happen. And we always have this problem of resources. So the question is, how should we test smartly? And really, who should we test? So that's really the question that comes around this. So let's look at it for a second from a machine learning point of view, because that's really what we're looking at. You can think about two populations. You can think about an infected group and a susceptible group. I mean, you really can think about more, but again, just to make it simple right now. And if I test it, then I know which are the red and which are the black. Okay. Of course, in reality, again, I don't know which one they are. So I have an empty set I have a set that is not labeled, and this is where I need to work with. So I need to decide how do I decide to test. Who do I test here? So that's really the question here. So what typically happens that I test only a few. So I decide to test, maybe randomly, maybe because somebody presents symptoms, maybe somebody belongs to some population, and I test, here too. So I tested these two, and I find that this one is maybe not sick, and this one is sick. So this is susceptible, this is not. And now the question is, what's now? Because then I have all the rest of the stuff, all the population that is not labeled. Well, the goal will be to start is to say, I know this guy and I know this girl, so now I can go ahead and I start estimating what are the rest based on the fact that I know these two. And this is, if you think about it, not a very new problem in some way, that you know only a part of the population, you try to get them all. We do it semi-successfully if you watch the results of the election last week, where we are sampling a part of the population, deciding what they're going to vote, and then look at the rest of the population and see what they're going to vote. We do it all the time in terms of sampling a few individuals and then trying to reflect for the whole thing. And the question is, how do we do that? And we'll talk for a second right now of how we do these kind of things. And this will give us kind of a background of how do we actually sample. And that's the important thing here. So let's talk for a second a little bit in more math. So we have a data set, it's X, where I have basically n individuals in this thing. Every x1 to xn is a vector, okay? And you can think about the vector as the properties of the individual. So in this, very simple example, every x is just going to be the coordinates of the dot here. So in that case, it will be the x1 and the x2. So it'll be the location of each one of them. But if you can think about, for example, infected people, then you can think about you can label the x's as where they live, what they do, what their age, who they're, everything that you can think. This garbage can X is a vector that collects every data that you have on that particular individuals. And then you have an associate labels. And the labels would be, each one of them will be either you're infected or not infected in that particular case. And then this is how you're going to do this. Now, what we know is we know X. So the idea is that we have a good idea of what is the data, what were the people we're actually sampling. We can know what their age is, what their affiliation, whatever we want to know about them. Of course, we don't know if they're sick or not sick. That's the thing. So now what we want to do is we want to compute an estimate of the true thing, y hat. So we have to remember, it's not the true thing. We're computing an estimate. Again, I think that the statistician had done a very bad job last week, and that really helps me to explain, to kind of put us this point, that all we're computing is an estimate, and it can be wrong, and it can be biased, or it can be something else, and we'll talk about this, and because it comes to any problem of estimation that we're going to do like this. Okay. Now we can sample from the data. So the idea is that we can sample from, we can decide that we're sampling from these X's and from the Y, but it's expensive, and we have only a finite budget. So the question is, how are we going to sample to have the most accurate estimate? Okay, so this is where I'm going to, what we're going to look at this. So this is, by the way, the main goal of active learning. Okay, so there is a bunch of papers about this with the recent review papers. And there are a lot of techniques to look around it. And I'll, for a second, address some of the things that are existing there. So some of the techniques are actually, let's call it, they're model-based. So what you do is you generate you assume that there is y is a function of x. And what you're doing is you're approximating this function by some kind of parametric model. I mean, people say non-parametric, but it's always parametric because we're in the computer. It just means that there is a lot of parameters. So you're going to approximate this function by a function of x and theta. Theta are going to be parameters that we're going to, in the machine learning world, learn. In the statistical estimation, we're going to estimate, depends on how you're going to do it, from the data. Now what we're going to do, we assume this relationship exists. Then you choose a subset of the data. How we're going to choose it, we'll talk about this. And now you have x that you chose and y that you chose. And then you approximate this function the best you can with that particular set, with all the things that we know about overfitting and the rest that you want to talk about. Okay. And then what you do is you go ahead and you use this estimation to try to estimate the rest of the things. So this is where you're looking at typical active learning approaches where it's model-based, okay? Most of the work that have been done on this have been on under-parameterized techniques. So if you think about it, for example, simple as linear regression, recently there have been work on over-parameterized, so deep neural networks. But again, you're coming from with an assumption here in mind, okay? Now, the way we looked at it is slightly different. And what we said, we don't want to use this kind of approach when we're parameterizing the thing. What we want to do is we want to use two steps. The first steps, we're going to just estimate the labels without actually having, we have a model, but the model is really not, it's not a parametric model in this case. And then we estimate the model from the ones that we actually labeled, okay? So the advantage is that we're separating it into two tractable problems. One is estimating y hat given y. We'll see in a second, this is a very tractable problem. And then what we're going to do is we're going to use the y that we got in order to train the system to get this step. So that's going to be a second step. And of course, we will have a lot of data at this point because we labeled a lot of data with this approach. So, so that's what we can do. And of course, we can use in this way to ensemble models. So for example, we'll not necessarily have one estimate of this y. We may have many estimates. We can talk about this a little bit later. Now, the same problem, I mean, the reason that I was excited to look at this problem about a year ago when we started was that this is a problem we actually have done for a very long time, and people here that have been involved in this, the problem of sensor placement is basically the same problem. So in experimental design and sensor placement, you basically have to measure some field. You can think about measuring a temperature field, for example, and you can't measure the temperature field everywhere. So the only thing you can do is you can go ahead and you say, I'm going to place the sensors in a few places, and I'm going to estimate the field everywhere based on these sensors. So this is really what we're coming from. And I've done personally a lot of work on this particular problem for experimental design in the past. And I thought this is a really good kind of connection between what people call optimal experimental design and active learning. These two communities seems to be living most of the time in different worlds and don't talk to each other. Basically, one is the Fox News, one is the CNN. I'm not saying who is who, but they don't tend to talk to each other, and then you see strange things happen. So let's kind of second review what do we do in active learning and how active learning and semi-supervised learning and all these kind of things are connected. So the first problem, as I said, I want to label all the data given a subset of the data. So I have a data set X and I have its partially labels. So I have this set of indices that are labeled. And I want to evaluate the whole set. I want to evaluate the labels over the whole set. Okay. The mathematical model we're going to use right now, it's definitely not a correct model, but it's a convenient model. And if people want to, I'll say, by the way, where are the problems in my talk, so you will know, so you don't have to really work that hard. The first problem we have in our talk is this particular model. So the model that we have right now, although a lot of people assume this kind of model, it's basically assumed that the data that I observe is going to be the true label plus some kind of error. And that's, of course, and the error is Gaussian out of all things. It's an incorrect model, again, but it's very, very convenient. You'll see why. People have worked, of course, on much more complicated models than this. When we experimented with more complicated models than this, we did not see much difference in the results. But this is the assumption we're working with, again, for mathematical conveniency. Now, of course, I want to go ahead and I say, now I want to estimate the whole y, given the fact that I measured y in a subset. Of course, the problem is ill-posed. I mean, I can't really, I have data that I did not sample. So I have to make some assumptions, and the assumption, of course, will determine how do I estimate the rest of it. Okay, so here's going to be the assumption that we do. What we're going to do is we're going to have a graph that represents the data, and you can think about it that you have links between. So here's my data, and you can ask yourself, the data is linked from each point. Now, as I said, I'm going to point to places that are problematic in this work. And the biggest problem, even though the graph seems to be mathematically, it's very clean, in reality, the graph is very, very, very not clean. In a sense, in L2, when I have like points like this in distance, it's clear that I can say, okay, this point is close to this one, and this one. So these are the edges that I have in my graph. And that's how you kind of build the whole thing. Now, in reality, which point is close to which point is actually determined by some distance function that we can decide about the distance function. And the distance function in reality is not necessarily very well known. So in the COVID cases, it's relatively okay because you can say that, for example, people that are exposed to each other should be linked in an edge. And you can actually estimate not too badly which people are linked to each other. In reality, again, for problems that are, think about, for example, the results of the elections from last week. The edge that can be taken from two individuals can be if they're linked to each other with some Facebook connection, and that's much more difficult to estimate who is linked to who. So the dirty or the dirty laundry is hiding in this distance function, really. And estimating this distance function or working with a reasonable distance function, that's really where it's difficult to decide. But this is not, what I'm saying here is not different than almost 90% or 99% of the literature that talks about estimating data like this, and basically say we have a graph. We assume we can estimate the graph. So by the way, sigma is a hyperparameters, and what you do is you estimate this graph. You put weights on the edges, and you get the graph Laplacian. So the assumption that we're going to have on the data is that it is smooth on the graph. Means that, for example, if this point is red, and this one and this one and this one are connected, then there's high likelihood that they'll also be red. That's basically what you're saying when you're saying things are smooth on a graph, or they'll be more red than dark, correct? So that's basically what you're doing when you're saying that things are smooth on a graph, and that's just an extension of what we know. Again, if you measure a temperature field and you'll say it's warm in here and cold in here, you know, if this is close to this, probably it's warm here as well. That's the only thing that you're kind of doing. There's nothing really amazingly interesting about this. It's just that the important thing to remember is that all we're trying to do is we're trying to assume that there is smoothness on the particular graph we have. So if you're assuming that you have a smooth graph, then you can go ahead and start doing your estimation. What you're going to do is you're going to say, okay, I'm going to estimate my y hat as solving a very simple minimization problem. And here you can see why I assume Gaussianity over here, where I look at y minus d, is my residual, which is assumed to be Gaussian, a weighting matrix W, which I'll talk about it in a second, times y minus d, and y transpose Ly is my Laplacian smoothing. And there is a regularization parameter, but it's kind of hiding inside the L here. It's not that important, as you'll see in a second. So now what is W? W is going to be a diagonal matrix with of a vector W. Now you can say like this: if I measure somewhere over there, if I measure the point, that can be, for example, 1. And if I don't measure, it's 0. So if I don't measure a place, it's 0. Don't use this data. If you measure, it can be 1. Or by the way, it can be anything else. I can decide I want to put any weights I want to put on that particular matrix. I can weight more points more, some points less. And of course, if I weight a point 0, then I don't need to measure it at all. So because we use, and by the way, the Gaussianity comes because I can use this model because of Gaussianity. So that's kind of the assumption here. So if I look at the estimate of y hat, now it becomes trivial linear algebra. And all you do is you add w to L, invert it, and multiply by w and get times d. So that gives you a linear estimation for y hat, the data measure. Easily do it. Again, function. Smoothness, for example, I talked about simple smoothness. Some people who are much more familiar than graphs than me should know that maybe you want a higher order smoothness. For example, you want to maybe do something like L plus alpha I to the power of gamma. So there are many computational issues here how to do this for large graphs, but these are all solvable, doable. To be honest, you need to kind of put a lot of numerical linear algebra in, but it's not very bad. I mean, we know how to do these things. Okay, anybody who've done reasonable sparse matrix computations know how to do these kind of problems. It requires work, but it's not impossible in any way, even for very big graphs. So again, if I want to do it for the whole population of the US, 360 million, I could probably do it on a reasonable workstation. For the Canadian thing, I could probably do it on my laptop. That's kind of put it in perspective. It's not like a super difficult problem. So let's look at an example. So here's my data. Okay. I labeled the red point here and the 2 blue points over here, and I go and I run my linear estimation here, and this is what I get back. I have to choose some parameters. I'm using them with cross-validation, and based on this, now I can train a neural network. So I can say, okay, now let's take the yellow point over here, the blue points over here, and use a neural network in order to train a network to estimate that thing. So if I train a neural network based on 3 dots, I'm going to be in trouble. It's going to be very difficult to train a neural network with 3 data points. But if I train neural network on all this, then I get some kind of an estimate. And we can talk about how good the estimate is. I'll say something at the end of the talk about this. But that's basically the idea that we have. So you don't have to train the neural network on this. You can train the neural network on this. Okay, so now we kind of think we know how to do semi-supervised learning. So semi-supervised means you give me a few data points, I get all the data points. Now the question is, what should I label? So again, I mean, here I decided to label this one, this one, and this one. And by the way, these are really done at random. I mean, this particular point, when we run this code, we actually run this on this example with random selection. We just made sure that we sample from one and the other. But of course, we know which one is which. We know that we have something here and something here. So we did make sure that we sample from both distributions. But the question is now, where should I run? Where should I sample for this? And of course, what you want to say is something very simple. I mean, the idea is that I have y hat, and what do I want? I want y hat to be the closest I can to y, right? So I want it to be the best. So the principal guide is to say, if I need to sample points from this, I want to get to sample points such that they will give me the best solution here. Of course, there's a chicken and egg problem. I don't know the solution here. If I knew, that would be great. But I want to sample from here such that it will give me the best estimate from here. But we can do something, as you will see in a second. Okay. But the guiding principle is see that you can get the best possible solution. That's the obvious thing here. So to that, what you have to do is you have to estimate the error in that you have when you're done the recovery. And again, the linearity here plays a big role. So you'll see why we went with this kind of very simple approach. So if I'm looking at the error between y and y hat, I cannot just look at the error as an independent thing, because the error, of course, depends on, I mean, y hat have errors in it. And remember that some of them are assumed stochastic. So I assume that some of the tests were not, I mean, we know they're false positives, false negatives. So I cannot really talk about just the absolute error. I can talk about an expected value of the error. So you plug instead of y hat the estimate, which is very straightforward. It's a linear estimate. And you basically say that d is y plus epsilon. Again, this is the easy part. And then you open brackets and you do a little bit of tricks here. It's not very complicated tricks. It's about 2 more lines of linear algebra here. And what you get is you get this expression that you can separate the expected value into a bias term, okay, and a variance term. So let me for a second say something about both terms. The bias terms really come from the fact that we assume that y is going to be smooth on the graph. So basically, if you think about it like this, if L times y is 0, so smoothness basically is 0, so you get 0 measure on the smoothness, then this term is 0. So the bias is really coming because the true y is not really smooth on the graph. It's maybe smoothish, so that is small, but it's not super small necessarily. So that's where the bias is really coming from. Okay. Then you have a variance. The variance really is coming from the fact that I have errors. So all these matrices are matrices. So this H is just the matrix we invert here. But you see there is this sigma, which is really the covariance of all these epsilons. So if I have no errors, if my y is exact, if the data that I measure is exact, the variance goes to 0. And then all I have is bias. Okay? Usually, now what you have is you can think that the W is something weights that we choose. One thing you can say is you're really small, and the bias will be going to 0. But what will happen then is, remember that the H, I need to invert it. And what will happen, it will become unstable. And in that case, I'll get very big bias. So there's always this trade-off between bias and variance. For people who've seen this before, it's not new, where you have to kind of choose your weights in a reasonable way such that the thing will be kind of balance itself. There is no free lunch. Okay, so we're always going to get either some bias, some variance, and now we have to balance between them. Okay, so that's a general error. That's the general error, the expected value of the error I have. Now, when we look at this expression, what we see is that it depends on a few things. It depends, of course, on the true y that I don't know, but it does depend also on the h, and inside the h there is the w, right? W control. W is where do where do I sample and how much weight do I give to every sample. So that's where I can actually control things, and this is where the experimental design comes. Okay, so again, look at this thing together again. So again, the variance has nothing to do with the true solution. Depends only on the way I'm going to estimate my weights. The bias depends actually on the true solution, which I don't know. So this part here, I'm not going to be able to estimate. I'm going to only be able to bound. And now I need to make some ideas. I need to say, okay, I don't know the true y, but I can do something with it. I need to bound it somehow, make some assumptions. And whatever the assumptions I'll make, that's as good as I'm going to get my solution. And by the way, when I made this talk, we were thinking COVID, but of course, given the last few weeks, looking at elections and what the statisticians are doing is not very far from this. And you can see that based on these assumptions that are done here, this term here is the term that's screwing up the whatever the statisticians are trying to do. So if you want to think about why are statisticians screwing up the results of the elections, is because they're making assumptions on this term. And again, they have no way to know what the true y is. So the only thing they can do is make assumptions. And assumptions that are based on maybe previous elections or previous things they've done, or common sense assumptions or something else. And every time they make the wrong assumptions over here, they would screw up the bias and they will screw up the prediction of the results. And this is where we're seeing all the time. Okay, so we can look at two different ways, two different sets of assumptions that you have here. The first thing is you say, let's assume that this y is a stochastic variable. Okay, and that leads us to something which is called Bayesian design. If you have a stochastic variable, then this is not going to become anymore a bias term, because bias per se does not exist in the Bayesian techniques. But what you do is that if you assume that y, to make it a little bit more interesting, is just normal with mean 0, and also smooth with L pseudo inverse covariance matrix, you can plug the whole thing in, and what you'll get is a very nice expression. One of the reasons I think people like Bayesian estimates is exactly that. You just all these kind of things shrinks to one thing, the trace of H inverse, and that's it. So the result does not depend at y at all. Of course, it does not depend on y because I assumed that y have a certain probability. So I assume that y have a certain probability, and everything shrinks to exactly this. Okay. And by the way, if y have this probability, then the estimate we just used is the map estimate. So the map estimate would have an uncertainty that is really coming, is this uncertainty here. Okay. So that's kind of one thing. The other thing you can do is you can go ahead and say, okay, now if I do that, I'm taking this problem that I have here. Okay, so a problem that I started with before, And I'm thinking about an objective function that is made from, again, from what I had before, and this is going to be with the assumptions, just going to a very simple expression here. And I think about it as a function of W. Okay? So if I want to minimize the uncertainty in my estimate, all I want to do is I want to minimize this function, which is, again, in the no assumptions on W is here, again, but with the Y in, that I don't know what it is. With assumptions on Y, with a simple assumption on Y and Gaussianity and with a certain covariance matrix is this one. And now I have to just decide what I want to do with this. So again, Y is the labeling process. And until now, I assume it's fixed, but I can, of course, say, let's try to choose W, and let's, again, choose who we're going to sample in order to make this thing better. Now, the solution, by the way, is obvious. Just sample everybody. So label all the data. If you label all the data, everything is, of course, the best you can get. But of course, I don't want to do that. I want to penalize every data sample. So we are changing the optimization problem for the Bayesian one. What we do is we say, let's minimize the trace, basically the uncertainty, and we trace, basically we add a penalty for each weight we're sampling. So the cost is going to be every individual that I sample, I pay a cost. This cost function right now, as you can see, is linear. You can decide whatever cost you want. I mean, the linear cost is kind of reasonable if you think about it, but you can say, I want to have a quadratic cost, or if you have a more complicated cost, you can just add it in. Just linear cost is kind of easy when you do this. So the sampling, of course, depends now only on the graph Laplacian. So the way you prepare your graph Laplacian, you do this. Now, the interesting thing, if you look at this, again, the solution of this thing has nothing to do with the true Y. I assumed some distribution of Y, and now that gives me what's the best sampling strategy here. So it kind of looks a little bit counterintuitive, because you'll say, wait a minute, if I'm sampling a few people, should I, and I got some results, should that change what I'm doing? And the answer is no. I mean, with my assumptions, the answer is there's nothing to change. The sampling here is independent of the solution at all, because the solution is assumed, again, the solution is random, assumed random by itself with a probability density function. So this is what you have. And in this example, for example, you see that if you have 4 clusters, the interesting thing is it will immediately hone on the right clusters to sample from the cluster that you have here and to get things right. So that's kind of the nice thing about it. Again, the not nice thing about it is that, as you see in a second, it does not really lend itself, the approach, the Bayesian approach, does not lend itself really to a multi-scale or something that when you sample a little bit and then you change your sampling based on what you got. So that's something that is not really happening in Bayesian design. And again, it's because of the assumption, because the strong assumption that comes here when you're making this assumption that Y has a certain distribution. But what happens when you do this, kind of put things in perspective, you can decide how many samples do I actually have. So this is sparsity, or basically assuming how many doubles do I have and what's the error that in my recovery. And you can see that the error kind of reduces as you increase your W. And maybe at some point you'll say, look, if you actually have a real limitation in terms of cost, you'll say, look, in the beginning I reduced my error quite a lot, and then somewhere here maybe it's not worthwhile for me to add more tests to just reduce the error a little bit. So this type of curve, this L curve type thing, is very typical to these kind of problems, and this is done by setting, changing the weight of alpha here, the weight here, the bigger the weight here, you're basically saying really focus. I don't have a lot of money to sample. As this is small, you say, yeah, just make this thing as small as possible, make the error as small as possible. Okay, so again, the drawbacks of the Bayesian active learning is that the Bayesian does not depend on Y and or the estimate. So you can estimate something and you say, what do I do next? Well, that's what you estimate, and that's done. So the a priori information we have, as we see in many cases, ignore the facts. So it doesn't want to confuse it. You don't want to confuse yourself with the facts. So you made an assumption about the estimate. Now you sample, you got your Y hat. And if your Y hat doesn't look at all like what you thought it is, you're kind of stuck here. I mean, you made an estimate, and this is just one. I mean, again, there is no real Y. The Y hat just represents the probability of Y. So, or it's a random sample from Y. So there is no real advantage of the active part of the learning. So you can't really think about increasing the sample size slowly and learning something as you go along. And this is where we want to go for a frequentist approach. So a frequentist approach is going back to the function and saying, now I'm not going to make any assumption on the y. So if I'm not, well, I'm going to make an assumption, but not this assumption. So that means that I'm stuck right now with this term. This term is the bias here stays here. Again, this term is easy, but this term is not, I don't know what to do with this in principle, because again, I cannot minimize it because I don't know anything about the y. So what can I do? Well, I mean, there are a bunch of things that I can do. One thing is that you say, let's say that I'm doing some initial estimation of y hat, and that can be done either by choosing randomly or by doing Bayesian design with a certain points, or do whatever. Then you can show that if you plug the y hat inside here, so you plug your estimate inside here, so again, it's not a true thing, then this is always smaller than this. So the estimate is doing better than the true thing. So one of the things you say, you know what, again, what I'm going to do is I'm going to solve a problem in a sequential way. I'm going to basically have a few samples, get my y hat, plug the y hat into here, okay? And after I plug it back into here, I'm going to estimate a new weight here. And that will give me, again, who to samples it. So every time, if you think about it, you're going to estimate, who is sick, who is not sick, or who is Republican, who is Democrat. You're going to say, okay, this is my estimate right now. You're going to plug it into here, and that will give you a new problem to solve, where you can increase the sample size. Now, because now it will tell you something about who do you think is the most important person here. Okay. So this is a test problem when we have again, two populations like this, and you can think about how the error of the sampling versus the random sampling. So random sampling and the active learning sampling starts kind of the same. There's just luck to see which one of them is better. And then as you start increasing the sample size, the active sampling become much better compared to random sampling. And again, because you're using information that you got, and in the random sampling, you're just adding information randomly about different things here. So that's really what you have here. So again, I mean, try to get a little bit of intuition. Again, more or less the things I've already said, is the main contribution of this function when you actually look at it is when this thing is actually large. So the bias is really the main amount of contribution to the function, as we have all seen last week. Again, if you look at the results of the election last week, the real reason statisticians screw it is not the variance, is the bias. And by the way, that's true for 4 years ago as well. If you look at it, if people talk about the fact that people did not sample enough the white uneducated. Now I heard yesterday the New York Times claimed there was not enough sample of the Hispanic vote. So it's really the bias. They did not believe that certain things in the bias term is really what really screws up the predictions here. So this is where the main contribution here. So what you're doing here is you're saying, look, if you look at this thing and this is large somewhere, then you want to sample where this thing is large more. So if you see that there is a high curvature, so things are changing quickly, where this is large, all you want to do is you want to sample more where things are actually happening over here. And that's basically what this thing is doing. So it's similar to adaptive mesh if you want to think about it in ODEs and PDEs. It's the same ideas. If you think, again, L is a Laplacian, so it's a differential operator. So when this thing is large, L times Y is large, sample a little bit more. We do it all the time in numerical PDEs, and that's exactly the same idea as the experimental design here. All these ideas are coming together in a very natural way in many, many different fields. Okay. The last part, which I'm going to talk less probably about, is now we assuming we learn this Y hat, we need to train a network. Okay, so what you do is you basically come with your parametric estimation of the function if you want to do some predictions. And you can have a regularization term here, which I did not bother writing. But the idea is that you have a loss that depends on your function of x and theta and your estimated y. You can think about a simple sum of square difference, but there is a small problem here. It's not so small, actually, it's a big problem. And this is where we have to, again, wave a little bit our hands and do something here. And the problem is that y hat is estimated y hat. It's not a true y hat, so it actually has correlated errors in there. So in principle, what you need to do is take, for example, least squares. You need to put the covariance matrix inside your least squares. And doing stochastic gradient descent with this is actually non-trivial. I don't know any real paper that does stochastic gradient descent with covariance, with dense covariance matrices. And that's something that you need to do. So there are techniques to do this. What we're trying to do is we're trying to approximate this H inverse with some kind of a sparse estimate, so we can take things in a kind of a natural way. I'm not going to go much into this right now, again, just because of shortness of time here. But here are some examples we're using. So this is an example with MNIST that we've used. Again, we look at the number of neighbors and the prediction. And this is what we have when we're doing it active learning with only 5 examples every time. So we take 5, then other 5, and other 5, and other 5, and we start looking at what happens here. And you can see the accuracy is better than, again, doing something which is just say, let's just take some kind of a balanced approach. So we just take 5, where every time we take 5 from different set of digits, and we're training on ResNet 18. Okay, and again, you can see that when you look at this thing, again, accuracy is better, and the distribution of also the labels is reasonable in the sense the wrong labels are distributed in the kind of a low certainty, but the right labels are with high certainty. We're comparing it with a recent paper by Gal when they looked at their technique, when they look at variance ratio and random, and look at errors. And again, I mean, we have much less points we have to sample compared to when you actually do all these kind of things. So to get at 10% error, we need only 38 samples. Here into 5%, we need 92 samples, where again, random needed 255, 835, and in the method that these guys presented, 120 and 295. So even though, and by the way, here's where I need to say something which is, I guess, important, even though the methods that we're using do not in principle fit the problem, because again, these are not Gaussian errors. We're looking at classification and not estimation. Doing these techniques gives you an idea where to sample. Again, I can talk more about this, but there is more justification than just saying, okay, we're using it because it's easy. You can think about this thing that this is just an estimate, and we're doing well with the wrong estimator. So clearly, if we're using a better estimator, we're using, for example, a softmax rather than an L2, we'll do even better. And that's work that, by the way, other people have done in different fields looking at this. So there is a justification to use the wrong model as long as it's reasonable, because it's solvable and it's worthwhile something. By the way, this is, again, not new to use the wrong model because it's easy. Most of us are doing least squares, even though the data is not least squares in many, many cases. This is a recent comparison with, again, a recent paper that I really like, by the way. Noah gave a very nice, if anybody wants to see a general presentation on active learning, Noah gave a very nice presentation on YouTube when you can actually look at this. And then we compare with their paper. And again, I mean, you can see that this is random. And again, we're doing better than these guys. So if you look at this, they're getting to above 0.1, and we are starting, this is like at 500 models, and we are starting, if you look at the previous here, much better than even their end of the curve is. So we're doing much better than these techniques that are out there right now. Okay. So I want to summarize. So active learning is the sexy cousin of optimal experimental design. Like everything in machine learning, optimal experimental design, known for many, many years, books on this, papers on this, for many problems. Active learning, for some reason, these two things did not really talk to each other much in the literature, but it's really the same problem with maybe a little bit different set of assumptions. Okay. What we decided is that separating the labeling and the training, we do labeling first, training after. The approach by, for example, these guys is doing it at the same time. So I think that that's a disadvantage. You're training a big neural network with very few data, hoping that it will give you the right thing. Here we're generating a lot of data, and then we're training our model. We're using the optimal experimental design framework. And again, I mean, optimal is a very old thing. Optimal for inverse problems is, again, I worked on this problem with Luis Tenorio over 10 years ago, so it's also not so new. But optimal active learning is the way we call it, because I think it's more faithful to give it like the original name of optimal rather than some other strange name. We've done a few numerical experiments. We are working on new ones. the most important thing, again, to remember is that all these things relates on the graph. And yes, the main assumption we're coming with to this whole business is the smoothness over the graph Laplacian. The rest, maybe you may not like mathematically so much. From a practical point of view, because we played with a bunch of problems, the most important assumption is the smoothness over the graph, which means that you know how to measure distances over your data over graph. If you're a mathematician, then L2 is always works. But if you even think about, for example, natural images, how do you measure a distance between two images is not a trivial problem. And of course, this is where people are doing optimal mass transfer differences. That's actually something very important. So for example, for some things that we've done, we looked at distances that are based on optimal mass transport. Choosing the right distance and labeling the graph you have in the right way and knowing which node is close to which node, this is where that's where the secret sauce of making this work is. You should be focusing in order to make these techniques work for really interesting practical problems. And I think with that, I'm basically done.
Well, thank you. Thank you for a very interesting talk. Any questions from the audience?
Yeah, I have a question. So thank you, Eldad, for your presentation. It was very nice. So I have a question with regard to the scalability of this approximation. I saw that you have like multiple matrix inversions for computing the. So what is the number of parameters that you have employed for making use of your method, by using your method? What is the largest number of parameters?
So not parameters, you're talking data, correct? So this is always the interesting thing about these things. So here, when you're doing this is parameters, correct? In here.
Yes.
But when you're doing what we're doing, it's the data. So the size is really the size of the data.
I mean, the number of variables, the number of variables that you have. The number of variables, yes.
The number of variables will be depend on the number of data you have, right? So because the W weight each data. So the number of variable will always depend on the number of data. We agree?
Yeah, I agree.
It scales with the data. The bigger the data set, because you have to look, I mean, at the end of the day, you have to choose which data you label. So it has to scale with the size of the data. That's one thing we should be clear about. Now, this is where the good news is. I mean, it's maybe good, maybe bad. It depends how you view matrix inversion, and this is something that I've done a lot of work with in the past. So I didn't feel really that problematic about this. So let's for a second ignore the trace because they're stochastic trace estimators.
Yep.
It involves. So let's look at this, for example, operation or this one. It doesn't matter. There's matrix inversions. So the sizes we're talking about. So let's say I want to do this for the whole population of the US, 360 million people, let's say, including. I can actually do it on a workstation with direct methods. So if you use software packages like MAMS or Paradiso, factoring the matrix and keeping the factor Cholesky, that's actually doable. You don't want to do it with direct methods. Again, for Canada, sorry, we're in Canada, what, 30 million? That's been. I can do it on my laptop with direct methods. So we didn't really have any problem in here. I mean, so far.
Yeah, my question is because I work on optimal sensor placement for data simulation. And I know that we have a lot of observations, so it's not that straightforward to say, no, I just compute the inverse or factorize and make it.
No, you don't compute the inverse ever. Never.
It's not in practice. Yeah. You can't do that, right?
No, you never compute an inverse. I mean, we teach this in any numerical analysis course. We never compute only matrix vector product.
No. I'm not saying that we're going to compute the inverse.
Talked about this?
I can't hear you. I mean, you have like it's like, no, speak.
Okay, so we never compute inverses, only matrix vector products. So for example, in here, you can clearly see it. I mean, I compute L times Y, then I have to compute the inverse of H times this. So I don't compute H inverse, ever. It's like a number one rule for every numerical analysis course we give. The same thing here. The trace of H inverse is approximated by stochastic trace estimator. I personally wrote a bunch of papers about it, but there are other people smarter than me. Probably they're in this crowd as well that wrote papers about these things.
No, I know that there are
never really.
I know that there are some numerical method. We never compute the inverse. That's I think the basis of our foundations, right? But even you talk about Cholesky decomposition. I'm saying that in practice, just to compute direct solution of the linear system without computing the inverse, just making use of forward and backward propagation, depending on the number of observations that you have, that computation can be intractable. I mean, my suggestion is that it's much better just to compute the precision matrix in somehow, in some sort. Maybe assuming some sort of the correlation function in space, because because precision matrices can be sparse depending on the structure that
I know the work. Yeah, I know very well what you're talking about. But actually, we are okay. If you want to be technical right now, we are actually computing precision matrices, because what is H? H is the precision matrix, correct? It's H inverse is the covariance matrix. So we are actually computing precision matrix. If you think about the graph Laplacian from a Bayesian point of view, again, it's like we should go back actually to where we talked about graph Laplacian, somewhere here. So this is the assumption of this thing is that L, well, inverse, I mean, it's not invertible because of the trivial null space, but you can think about L pseudo inverse is really your covariance matrix. It's a dense covariance matrix. So the Laplacian, the graph Laplacian, is a sparse precision matrix. So that's exactly what's happening. But again, computing a precision matrix still is a problem. You have to solve it at every time. Again, big problems, you can always use something like conjugate gradient. I've done that before. You can use multi-grid methods to invert these things. I mean, again, all I say so I work with a postdoc on this thing, and at some point we looked at all these problems, and I said, look, I mean, we're big kids these days. I mean, we've all worked on these kind of techniques of using multi-grid methods, sparse matrix computation. We need to use these things. They're not trivial, by the way. I mean, they require work, but we know what to do. It's not, these kind of problems are not like untractable for us, even for very large numbers.
Yeah, I see. Yeah, I would like to discuss later with you this, because I have compute precision matrices of millions of variables, because it's weather forecast and it's tractable and it's very, very fast in comparison with traditional methods. So I think we can have some discussion in that direction. Thank you very much.
I have it's a really nice talk. I like this, and semi-supervised learning is close to something I worked on. But let's say I'm interested if if let's say you decide to take more and more labels, right? Because I noticed that you're having hundreds or maybe even thousands of labels in the end. So I expect that there is a limit that as you're sampling more labels, you're actually sampling out of some measure whose density depends both on the measure that you're sampling and the actual true function y. Do you have any idea as to what are you sampling in the end? Or, empirically, if we don't go into theory, I just am interested empirically, when you see the new points that they're coming up, are they getting close to the decision boundary, or are they getting close to the regions where there are no other points? What is that you're observing?
You're observing, okay, let me go actually back to what I kind of said this at the end, but you are observing, no. Where was it? Somewhere here. So what you're observing, especially with this approach, which I like much better. No, I don't like the Bayesian approach so much. Andrew Stewart is not here, correct? So I'm okay. I don't like the Bayesian approach that much.
But this is also something I understand better, right? So
you understand, okay? But so the thing is this: I am not understanding better. I mean, the mathematics of Bayesian methods is very nice. In practice, I don't understand it because the assumptions are coming from a probability. I mean, you're assuming something about probability and the probability of the y, which I'm not really clear about. But here, you actually see it very well, that you're measuring closer and closer to the decision boundary. That's what I try to say over here, because if you think about it, where this is going to be large, it's going to be large next to the decision boundary, correct? It's not smooth. It's where I'm far from the decision boundary, all the labels are the same. So the Laplacian of labels that are the same is 0. The Laplacian of things close to the decision boundary is very high. So what happens, in order to make this term smaller, the bias smaller, you need to sample closer to the decision boundary. And that's what you see all the time. You're immediately you're honing very quickly on the measuring to the decision boundary rather than measuring like some kind of uniformly over everything. That's what happened with this approach.
Thanks. Yeah, that's a good point.
Yeah, other questions? I have a question. So this Laplacian of the graph, does it depend on the properties of the graph, maybe sparsity or connectivity of the graph, and I mean, does it depend on the spectral, the spectral property of the Laplacian?
So again, I mean, the Laplacian is where the dirty laundry is hiding. You have to. It depends on whatever you want it to depend, right? I mean, I'll go back to maybe the beginning somewhere. Here. So, I mean, this is a standard way to think about the Laplace, the weighted Laplacian, correct? I mean, all I do is I put a weight over an edge, and now, for example, you can have a completely dense graph with everything connects to everything with different weights. So if you think about the dense graph, it just means that the one that is dense means that there is weight between each one of them. It could be close to zero, but there is a weight. So the real question is, how are you going to label your graph? And again, it's a question that mathematicians tend to escape it because, of course, it's obvious. I mean, you just have a distance function, and we'll just use the distance function, we put it in. And anybody who have seen lectures on graph Laplacian, you kind of usually ignore that particular interesting question. And again, graph Laplacian for points in L2 or L3 or R3, or it's easy. I mean, you go ahead and you sample your things. But the minute you start taking a real problem, you realize that, again, that this is really where the boundary is hiding. If you wanted to do the same approach here to label Democrats versus Republicans, you'll realize that you're running into trouble. You realize that, making decision, what is this vector X that I'm having here? So the vector X can be your gender, your age, your level of education, your ethnicity, or everything else. And now, how do I know what's the difference between two people? So who is closer to who? That's not 100% clear. Maybe some things are clear, but some things are not. And the fact is that we see all the time that the statisticians are screwing up with this particular things. So when we look at why do people do not manage to do this well, it's really hiding in here. It's really hiding in this particular thing. And again, I mean, I'm not different than anyone else, and I think the only thing that I'm trying to say that I'm different here is that I'm telling you where the dirty laundry is, and I think this is where you have to think to use these kind of techniques much, much, much harder. There is a tendency, especially for students, is to take the code and say, okay, let's run it and everything will be fine. And I have a feeling that also statisticians do this kind of thing before the elections. It was kind of interesting, again, because we did this work and looking at the results before the elections, I tried to read some of the more professional literature to see what are the statisticians are doing to address this problem. And to be honest, even with the Nate Silver, I have not seen any real discussion about how to deal with that particular bias. And what are they doing to try to see that they don't have a bias in their graphs? Because that's what they're trying to do. They're trying to somehow estimate the rest of the population given a small sample. So there is a big question here. Again, I don't have the answers. I wish I had the answers. Then I would be able to predict the results of the elections much better than everyone else. But I don't have the answers.
Thank you. Any other questions? Okay. If not, I guess we can close the session. We have a question and answer and discussion opportunity at the Gather Town link, and we'll be back here at 1:40 p.m. for.
And I have to apologize that I'm not going to be available for the question and answer because I'm actually, believe it or not, going to go on a plane today. But anybody wants to talk to me or stuff, I mean, I'll answer happily every email that will come.
Excellent. So we'll be back here at 1:40.